Okay. So section 11.7. In this section, we're going to discuss all kinds of problems. And we are not given specific method to solve the problem. Okay. So, let's begin with the following problem. This general, let's see, what is the formula for the general term? Okay, so this is m from 1. So n from, actually n from 2. Okay, this is a negative 1 to the nth power minus 1. And this is a bn. Let's say, what is bn? Bn is so n factorial, and 1 times 3 times 5 is the product of all those other terms. Okay, so when n equals 2, that'll be 3 factorial over 3, right? Yeah, so for example, when n equals 2, let's see what is so when n equals 2, that's 2 factorial. 1 times, so it's 2, 1 times 3, right? Yeah. So let's start from here. Okay. All right, so you see a series like that. It's alternating series. So it's natural to use alternating series test, right, to prove it is convergent. Now, alternating series test, you cannot use that to prove it's divergent. Okay. So what are they going to do with this? N factorial is on the top, right? Do you think the number approaches 0 or not? If the number does not approach 0, Bn does not approach 0, then it will stop there because it's divergent. So you have to check whether whether Bn convergent to 0, right? So that's first thing. In order to prove it is divergent or it is convergent, you have to make sure this limit is going to be 0, right? So that's my first question. But it's not easy to prove that, as you can tell. Okay. Yeah, so how do you can see, right? You have n terms, 1 times 2 times 3, all the way to n. And here's 1 times 3 and times 5, all the way to 2n minus 1, okay? So each term, okay, and you will see that each term less than 1, clear. The question is whether this approaches 0. I think this can be approaching 0, but it's not easy to prove, okay? The reason is, look at the last fact, right? This is going to be 1/2. The one before that maybe is also about 1/2. Then you keep, you take a few of them. Its argument, it's very different. It's not easy. Okay, not everybody can prove here in this class to prove this is a limited there. So using this kind of misleading. If I put this problem on the test, if you think you're going to use an alternative series test to prove it's convergent, then you have to prove the key step. You have to prove this limit is 0. Okay. Not only that, you have to also show that the Bn decreasing. I think Bn decrease is very natural because Bn is positive, limit is 0. It must decrease. Otherwise, the limit is not going to be 0. All right. So it's not easy to prove. Okay. It's not easy to prove this limit is 0. So what is our other options? The other options is, okay, this is going to be an, right? The other options use a ratio test. Okay, so an plus 1 over an is the absolute value. Okay, if this limit is less than 1, then it's convergent. So let's try. Okay, so an plus 1. So you have 2n and n plus 1, right? And this 1 times 3 all the way to 2n minus 1. The last term was 2n plus 2 is 2n plus 1 here. Now the denominator, and it's going to be upside down. 1 times 3 all the way to 2n minus 1. And this is going to be 1 times 2 times all the way to n, okay? And then you will see that you can cancel them. What is left is n plus 1 over 2n plus 1. And the limit is 1/2, okay? So that means this is going to be L. L is going to be 1/2, which is less than 1. Then by the ratio test, okay, the ratio test, this series, okay, and this series even convergent, okay, is convergent. So of course the original series is absolutely convergent, even can get, yeah, this is absolutely convergent, okay, it is absolutely convergent, okay. So if you use a ratio test, you even get more information about the series. Okay, now so if you really want to prove this series, the limit of Bn approaches 0, and you have to look at this this term. So k is 2k minus 1. Of course, the limit is 1/2. So the question is, when it's, I'm not going to, the limit is 1/2. It's between 1/2 and 1. Let's say 3/4, right? 3/4. So the question is, for what the value k is this going to be less than 3/4? Well, you can solve this inequality. 4k less than equal to 3 times 2k minus 1, 4k less than equal to 6k minus 3, right? And that's why 3 less than equal to 2k, 3 over 2 less than equal to k. So actually, when k is greater than 2, it's already, it's less than 3 over 4, okay? When k is greater than 2, that's enough, okay? When k is greater than 2, this is less than 4. Now, why this is useful, okay? So Bn, let's take a look at 1 over, right? 1 over 1, right? Now let's go back, right? This is mine. And the 2 over 3, right? Okay, and the 3 over 5, right? And I think here's 2n minus 1. I think all those terms will be less than equal to 3/4. I think after k is greater than, keep, 5 over 3, start from here, all the terms will be less than 3/4. Okay? Right? That's what we already proved. Okay, when k is greater than equal to 2 over 3 is actually not less than 3 over 4. Right? Now this is actually also already less than 3 over 4, but that's okay. We don't need it. Okay, so 2 over 3, and then be 3 over 4. 3 over 4. Okay, how many of them here? N minus 2 many, right? Okay, and clearly this approaches here, right? So this is another way to prove. Then you have to prove that the Bn decreasing. Okay, Bn decreasing. If you want to show Bn decreasing, you have to prove that this is less than 1. Okay, you have to the last. You see the ratio, right? So you get this one. Okay, so so bn plus 1 over bn is going to be n plus 1 over 2n plus 1. Now the question is whether this is less than 1, because then it's decreasing, right? Right, and that is clear. N plus 1 less than or equal to 2n plus 1. Yeah, that's always satisfied. So that's why bn is decreasing, and the limit bn is 0. Therefore, the series is convergent by the alternating series test. But I said that not everybody are able to get this part. Okay. Okay, not everybody can get this part. So, it would be the best choice to use a ratio test to prove it's convergent. Okay, even you can get more information about the series. It's absolutely convergent. Okay, but does not mean you should give up, as a possible way to solve a problem. Especially as a math major student, you should try all the possible ways to solve the problems. Okay. This is a basic requirement for math major students, how to estimate, get another simpler, but convergent to 0. Okay, simpler term, but convergent to 0. Okay, let's take a look at the next problem. This is every time I give you a minute to think about. Okay. So look at this one. I know you can solve the problem, test for divergence or convergence. The question is how many methods you can use to prove it is convergent, for example. Okay. Yeah. Right. Yeah. You think about what are the possible ways to solve the problem. Okay. Let's go over all the possible methods, right? Comparison test, limit comparison test, integral test, ratio test, right? Alternating series test, root test. Okay, I give up the ratio test and root test because I don't see explanation function there. I don't see n factorial, right? Integral test, usually it's not easy to use. You have to evaluate integral, right? So we use the integral test only for that to prove some tests such like a p-series test, okay? So that will be my last choice because it's complicated. So comparison test or limited comparison test may be the best choice, right? Okay, but you have to compare it with something, right? So let's take a look at A. I think for this particular problem, I just use a comparison test because it's less than or equal to n. Then I enlarge the numerator denominator. Then I get 1 over n squared. Okay, that's my bn. Okay, And then on the left, this is always positive, right? Not negative. So this is going to be less than or equal to 1 over n squared, which is finite. But you have to say that by the p-series test. And this is you don't need to prove that. Okay. So therefore it's convergent. Okay. So my conclusion is convergent. Okay. Now if I modify the problem a little bit, okay, then you cannot use a comparison test. It's not easy, okay? Because n plus 1 is not going to be less than or equal to n. But you still compare it with 1 over n squared. What they do is usually use a limited comparison test. You have to, for a limited comparison test, you have to find a limit. So you drop all the other unnecessary terms, right? Drop 1 and plus 1. This is a 1 over n squared. That's my bn. All right. So you can find the limit, okay? And that is always going to be 1. Now, if this procedure is just drop the constant, then you don't change the limit. The limit is always going. Okay. Therefore, n and bn have the same convergence. So since this is convergent, it's convergent, right, by the p-series test. Okay, you don't need to prove that. We conclude that, okay, we conclude that this is a convergent too. Right, and by the limited comparison test. Limited comparison test, okay? Yeah. You can also use a limited comparison test to prove, to solve the first problem here. But I just said that you have to find the limit. Okay, that's all you needed to do, right? You have to find the limit. The limit I just claim here. The limit, if you really want to find the limit, and this you have to put the right details here, and this will be n squared over 1. Okay. Now the question, what is the limit, right? So numerator is polynomial degree 3, denominator is polynomial degree 3. So you divide numerator denominator by n cubed. So it's 1 plus 1 over n, and here plus 1 over n cubed. That's what you get, right? So the limit is going to be 1 plus 0, 1 plus 0, which is 1, okay? So you have to find the limit. I know even the limit is going to be 1 because I just delete, those constants. But you have to give a proof, or you have to say a few words. It's obvious, right? All right. Okay. But if you want to use a comparison test, it's not easy to find. Let's see. You cannot compare with this one directly. If you really want to compare, maybe this is not going to be less than or equal to, right? But if I make it larger, I put a 2 here, maybe it's still true. Okay. The reason is, okay, you can double check because this is make it larger because here's n plus 1 there. Okay. So how do you check? Right? Use a cross product, right? So n squared n plus 1 less than 2 n cubed plus 1. So you have n cubed plus n squared less than 2 n cubed plus 1. So it's not very clear because you have n squared minus 1 less than n cubed. So this inequality, who knows, right? Right? Yeah. But actually this is true. The reason is, n squared minus 1 is less than or equal to n squared. It's less than or equal to n times n squared, which is n cubed, right? Got it? So, yes. So therefore, the above inequality holds. Then you can use a comparison test, but it's not easy to find the right BN. Okay. Okay. So I modify this problem again. I put this is n minus 1 and cube plus 1. This is alternating series. Right. This is alternating series. Yeah, please think about what are the possible ways you can solve the problem. You list all the possible methods. I can tell you this is convergent. I think it's obvious it's convergent. All right, let's see, what do we get? I cannot use n-sum term test to prove it's divergent because it's convergent, okay? And the comparison test, no, because comparison only works for series with non-negative terms. Integral test, no, definitely it's not, okay? So use a ratio. Yeah, you can use a ratio test, maybe, but it's not working. Okay. I think the only choice is alternating series. It's the only choice, maybe. Okay, but there is another theorem in the section, in the last section. Okay, if we can prove it's absolutely convergent, then it's convergent, right? So actually, there's two methods here. This is my n. If you look at the absolute value, then this is n minus 1 and cube plus 1, right? As I already told you, for this one, you can use then you can say that you can apply the limit comparison test, okay? This is a convergent, as we already showed that, by I put the limit maybe because it's not necessarily limit comparison test, right? See above argument, right? Yeah, okay, so I skip that part. Therefore, this series is convergent, okay? So that's the first method. Second method, actually this is better, okay? You can only apply a comparison test to the series like that. You remove the negative sign, right? Now the second method is alternating series. And you have to prove that this is clearly this is decreasing. This is the limit is going to be 0. It's obvious, okay? The limit is going to be 0 because the denominator is polynomial degree 3. And you can you can divide both sides by n cube, right? So the limit is 0 over 1 to 0, okay? Why it is decreasing? Why it is decreasing? It's not clear. The only way you can prove it's decreasing, you have to change it to the function. So where the function is going to be x minus 1, x cubed plus 1. I'm pretty sure it's decreasing for large x. Otherwise, it's not going to converge into 0, right? So all I have to do is just find the derivative. Okay, it's x cubed plus 1 square. Okay, let's simplify it. It's a 1. X cubed plus 1 minus x minus 1 times 3x squared. Okay, right? This is the derivative. Here, x cubed plus 1 squared. Okay, let's multiply this out. It's minus 3x cubed plus 3x squared. Wow. So it's 1 plus 3x squared minus 2x cubed. And why this is going to be negative for large x? Because for large x, right? The leading term here is negative 2x cubed. So for large x, this is going to be negative. Okay. Now, for what x, x greater than some equal to some number, right? Okay. How do you see this is negative? I can think about it. How about replace 1 by x squared? Because this is true if x is greater than 1, right? Because the x is less than x squared. Now 1 is less than x squared. Okay? Then if you do that, that's so easy now. Right? X cubed plus 1 squared, then I take x squared out, take a 2 out, that'll be 2 minus x. Right? And clearly this is going to be less than 0 if x is greater than 2. So if x is greater than 2, this is going to be less than or equal to 0. Okay. That's all we need. But this is a trick, right? This is a trick. Okay, it's not easy to figure it out. All right, so that means Bn is f of n is decreasing for n greater than 2. That, so therefore this series is convergent by the alternating series test. Okay. So you have to prove two things. Bn decreasing for larger n. The limit of Bn is 0. Because those are two properties that are required to prove actually this alternating series is convergent. Okay. That's why we wish you to understand the proof for each of the tests we're using here. Okay, because if you know how to prove it, you know what is required. So when you do a specific problem, you will not forget to check all those conditions. Okay, now you have a textbook open on your table. So you can easily, you don't need to memorize that, all right? That's great. So you just needed to check one by one all the conditions given in the statement of the test. Okay, so there are two possible ways to solve this problem. I like the first one. You see, it looks much shorter, right? It is much shorter. If I change it n minus 1 to n plus 1, it's much shorter, right? And if I put a problem, here n and right, and I think is still the easiest way to solve this problem is use a comparison test. Okay, but you have to prove that it's absolute convergent, because when you put absolute value and you get n cubed plus 1, which is less than or equal to n over n cubed, which is 1 over n squared, that's Bn. Okay, then apply the comparison test. don't forget this, it's less than or equal to, okay? This is a finite. Okay, that implies this is absolutely convergent. Yeah, this is absolutely convergent because the series of absolute value of all the terms is convergent. Okay. Why this is a convergent implies that one convergent? Well, we have to prove that. Okay? We have to prove that. Okay? You can go back to look at the proof if you want. All right. Yeah, let me ask you to work on this problem. So remember, lots of problems here, it's like alternating series, but does not mean you have to use the alternating series test to prove it's convergent. Okay, so given this series, okay, yeah, I'll give you a half minute to think about possible ways to solve the problem. Or maybe 1 minute, okay, give it 1 minute, okay. Okay, I hope you got some ideas. I think clearly this is going to be convergent, but it's alternating series. So try alternating series test first. It's complicated, but that should work. Okay. So here's a Bn, which is n over 3 to the right. We want to prove this decreasing to 0. We have to verify this one. I think it's decreasing. It's the limit to 0 is obvious, right? The reason is the denominator is a limit. It's the exponential function. But well, if you want to prove that, probably just use a function. Okay, f of x is going to be x of 3 as well. So the limit as x approaches infinity, we can use the Lupitus rule. and that is going to be 3x to the natural log of 3, okay, which clearly is going to 0. Okay, great. All right, so that implies the limit. The reason I want to introduce a function is because I really want to prove it's decreasing. So I have to prove that it's decreasing, right? Okay, for some larger n. So to prove this, you have to show that the derivative of the function is negative. Okay, 3x to the 1, it's 3, and here's a 1. 3 to the x plus 1 minus x. And the derivative of 3 to the x is 3 to x natural log of 3. Wow, how can I see that? How can I see that? This is again the 3 to the x plus 1 minus x natural log of 3 and then 3 to the x. Do you think it's easy to show this is negative for larger x? It's not easy, right? But the same trick here, I want here 1 plus 1. I want to change it to 3 to the x. Right? Then I can take the common factor out. Okay, so there's a trick here, right? So otherwise, how do you know this is going to be negative? Okay, so I take 3 to the x out. I have a 2. Okay, then for larger x, this is going to be negative. For large x, this is going to be negative. So this is going to be negative if x is greater than or equal to 2 over natural log of 3. Now the question is, what is 2 over natural log of 3? Right? You can use a calculator to check. I think this number is not big because natural log of 3 is greater than or equal to 1. So this is okay when it's greater than 2. Okay, just because you have this one. Okay. All right. So now we conclude that Bn decreasing for n greater than or equal to. Okay. Then so this series is the series is convergent by the alternating series test. All right, what else? Is there any other way you can show this is a convergent? Right. I think the difficult part is prove it's decreasing, right? Now use a derivative, you still have to show the derivative is negative. If you do not use a derivative, are we able to prove that this is going to be less than that, right? So it's going to be, we got to the original function. Yeah, okay. So where's my function? It's n, right? Yeah, so this is n over 3. Okay, n and then turn upside down be 3 to the n plus 1 over n. Okay, so this is going to be n plus 1 over n. And here's 3 to the n plus 1 to 3 to the n plus 1 plus 1. Right? Now, I know the limit is going to be 1. It's going to be 1/3. How do I know that? The limit is going to be 1/3. Well, the limit of this first term is going to be 1, right? It's 1 plus 1 over n. The second term I divide by each divided by 1/3 to the n, right? Yeah, divide by 3 to the n. So I get 3 plus 1/3 to the n. So the limit is going to be 1/3. Of course, this is going to be the limit, right? So that's why for sufficient large, for large n, this is true for some large n. I don't need to know when, okay? So that's another way to prove it's decreasing. But if you are able to find the limit, why not use the ratio test? Because when you see exponential function, you can use a ratio test, okay? So let's go back to this problem. I'm going to copy it. Okay, so this is n, 3 to the n plus 1. So this is my n, right? You consider this ratio, and that's what we got here, right? And this is actually bn plus 1 bn, and we already found out the limit. And this is 1/3. 1/3 is less than 1. So therefore, n start from 1 to infinity. This is a convergent by the ratio test. Okay, so then original series is absolutely convergent. This is my n, right? It's absolutely convergent. Okay. I think use the second method is better. Okay, you don't need to worry about, you don't need to prove this decreasing the series bn. All you have to do is just the limit. It's less than 1. Okay. So the ratio test is that. So most of the problem you have to, whenever you see alternating series, okay, whenever you see an alternating series, you can try to use alternating series test first, or you can prove it is absolute convergent using ratio test or road test. All right. All right, so now this is n to the 2n, n plus 1 to the 2n. Is it convergent or not? Okay, 3 to the n. Let's change to 3. Okay. Yeah, I think it's convergent. The question is how do you prove? Okay, what kind of method you can use? All right. So please work on it. right. So first of all, you look at, right, this is not the alternating series. I forget that one. Forget the alternating series test. If it's divergent, you can prove using nth term test. Okay, it's possible, but it's harder to tell whether this is convergent zero or not. More likely it's convergent zero. Okay. Integral test, forget it, right? If you change n to the x, it's a very complicated function. So what is left, comparison test, but it's harder to compare with anything. Okay, so then you use a ratio test or root test. Okay, or root test. Okay, I think the best way to do is use root test because this is all of them are exponential function. Okay, so the nth root, right? So you can, what you get here is n to the 2n, n plus 1 to the 3n to the 1/3, right? Then that is going to be n squared, n plus 1 cubed. And clearly, the limit is going to be 0, okay? So the limit of the nth root of the nth term is going to be 0, which is less than 1. Therefore, the series is convergent, absolute convergent, because all the terms are not named by the root test. Okay. If you can use a root test, more likely you can use a comparison test because the whole proof, okay, for the root test, okay, you actually using the ratio comparison test to prove the root test. So if you sometimes it's easy to use a comparison test to directly, okay, because n is going to be n to the n, right? N plus 1 to 3n. So you can express in this form, right? Now, what is the inside? This inside is going to be, the limit is going to be 0. Of course, you can make it as small as you want, okay? So you can enlarge it, right? It's going to be n cubed, right? Right, and that is 1 over n. And I want to make sure it's going to be less than 1/2. That's enough. So if n is greater than 2. Now, if based on this simple observation, you will get 1/2 to the nth power. Wow, now you can use a comparison test, right? So that's why you have, let's say n start from 2. And this is a convergent by the geometric series test, right? We have 2 specific tests. This is geometric series test, P-series test and geometric series test. So, so that's why the series is convergent, okay? By the comparison test, and this is convergent. By the comparison test, okay? You have to give every conclusion. You have to give an argument, okay? Or you can quote a test because those are already proved in the book, so you don't need to repeat it. Okay, just quote it. So this is a complete argument. Okay, remember you always act like a lawyer in a court to trying to convince people this guy's criminal. Okay, so this guy is convergent, right? This series convergent, this series divergent. You cannot just say, "Oh, I feel like he's convergent." Okay. So every claim you have to mention, provide evidence, like here I provide evidence, right? And then I still have to quote the geometry series and the comparison test. Geometry series test and comparison test to prove this convergent. Otherwise, I have to go through all the arguments again repeatedly, right, to prove it's convergent by the original definition. Convergent means the limit of partial sum exists and finite. But that takes too much time. So that's the reason you just quote some tests. Okay. I think the most challenge part of this chapter is this kind of argument, how do you know, how to simplify the algebra expression so you can get upper bound, a simple upper bound. This kind of training, right? It's easy to understand, but it's not easy to do it by yourself, okay? If you did not build up a very solid math background in middle school and high school, okay, then you do have a little bit trouble. So it's better to use the load test directly, just like an engineer, apply the formula here and go and find the limit. Although you need a little bit of mathematics here, but it's easier to find the limit than to find the upper bound for the series. Okay. Yeah, I'm sometimes, some parents ask me to tutor their kids. I do find a very good one. I think he's a fifth grade. He already finished all the math up to ninth grade. I did a lot of exercise, clearly. Yeah. So this kind of, I think he's watching my videos of calculus because he already learned trigonometric geometry. All right, so next problem. Let's look at this one. Okay, this is again, you see many problems here are alternating series. Okay, alternating series. But does not mean you have to use the alternating series test to prove it's convergent. I think that this is a convergent. Okay, the easiest way to prove it's convergent is to use the ratio test because I see the exponential functions here. I can even prove it's it's absolute convergent. Okay, so let me finish that problem. Then we're done. Okay, you can the easiest way to solve this problem. This is n. So let's try to use trying to find this limit. So negative sign is gone. So n plus 1 square and 2 to the n plus 1. And the denominator right now is going to be up here. So after simplifying, n plus 1 square over n square, and here's a cancel 2 to the n, right? So this is 1 plus n square half, and the limit is going to be 1/2, which is less than 1, okay? So the limit is going to be 1/2, it's less than 1. Then you can see that this is a convergent, okay? And if I want to save time, I just remove this absolute value symbol, and I can put absolutely convergent by the ratio test. So for many alternating series, you can prove the convergence by the ratio test. Okay, you can prove it by the ratio test. Now, if you really want to use the alternating series, and this is a pretty challenge, okay? I forgot to go, yeah, n minus 1, right? N squared to n. So your Bn is n squared over 2 to the n. What do you have to do? You have to do that. This is the f of n, right? So f of x is, you have to prove that this is decreasing to 0. So you have to prove that's decreasing. So decreasing, you need to find the derivative again, right? The derivative is 2 to the x squared, right? And here's 2x, and 2 to the x minus x squared, and 2 to the x natural log of 2. Not too bad, right? You take the 2 to the x out, and I also have to take the x out, then have a 2 left, then have a natural log of 2 and times x. So when this is going to be negative, this is negative if x is greater than 2 of natural log of 2. Now, I don't know what is that number. You can use a calculator to estimate, okay? So when that is going to be, this number definitely it's less than 2, so it's less than 10. So you can say when x is greater than 10, this is negative. So that means Bn decreasing when n is greater than 10. Okay. You also have to look at the limit f of x and use Lupitus rule, right? It's going to be x squared, right? It's 2x, 2 to the x, natural log of 2. Then you have the differential again. And then have a 2 to the x, natural log of 2 squared. So this clearly the limit is going to be 0, right? So that means Bn approaches 0 as n approaches infinity. Then you can conclude that this series is convergent by the alternating series test, okay? So there are 2 different ways to solve the problem, but it's not easy always to use the alternating series because you have to verify these 2 conditions and you have to find the derivatives and find the limit, okay? I'm going to stop here. Let's take the